So, hi everyone, welcome to another LIC class. In the previous class, we started with the limitations of op amps, practical limitations of op amps, and one limitation that op amps have, which are very important, are their frequency response. The op amps have limited frequency responses, and a desired op amp should have a maximum frequency response. So it's always desirable to increase the frequency response of an op amp. We spoke a little bit about what determines the frequency response, the cutoff frequency. We have two cutoff frequency. We have the upper cutoff frequency and the lower cutoff frequency. And the lower cutoff frequency is determined by the coupling capacitor. The upper cutoff frequency is determined by the internal components of the op amp itself. We do not have any control over the upper cutoff frequency, but we can change the lower cutoff frequency by adding or removing a capacitor. If we do not have any capacitors in the input of a op amp, or in other words, we don't have any coupling capacitors, the frequency of the op amp could go down to 0 hertz, or in other words, it could go down to a DC signal. The frequency, the upper frequency of an op amp is determined by its gain bandwidth product, or we call it F unity. And the gain bandwidth of a system, again, we cannot change the gain bandwidth, but we can pick an op amp that has a higher gain bandwidth product. Another way to control the frequency response is by adding feedbacks. Adding feedback would most definitely reduce our gain, but it's going to increase our frequency response. So there's a trade-off on how much gain we need and how much frequency response we need. An op amp with no feedback, or in other words, an open loop op amp, has minimum frequency response. So you can see here the frequency response is very, very narrow. Go back to that slide. It's a very important slide. So the frequency response for this open loop is only 10 hertz. But if we add a closed loop system, the frequency response, it goes up, significantly increases to, for example, here to 10 kilohertz or so. So 1,000 times. But at the same time, the gain would drop. Sometimes drop in the gain actually is a good thing, because in an ideal open loop op amp, the gain is infinite, and an infinite gain would cause the output to go into saturation mode. And if you give like a sinusoid to an open loop, then the output you would have a pulse or a square signal, because it's going to be saturated and capped at the positive VCC and negative VCC, which are the supply rail voltages. And we don't want that to happen, because that causes a signal distortion. We are giving the signal one thing and we getting something else. We're giving it a sinusoid signal and we're getting a square signal. The upper cutoff frequency is measured and calculated using the gain bandwidth product. And the equation was F2 is equal to gain bandwidth, or F unity, over A noise. A noise for an inverting and a non-inverting op amp is the same. It's equal to 1 plus the feedback resistor over the input resistor. So 1 plus R2 over R1, or RF over R1. So regardless regardless of the type of op amp that we use, if it's inverting or non-inverting, A noise would be the same in both, but their voltage gain would be different. For an inverting op amp, it's negative RF over RI, and for a non-inverting, it's 1 plus RF over RI. For a non-inverting op amp, A noise is equal to the voltage gain, but for an inverting op amp, it's different. We solved some practice problems, some examples for a single stage and calculating upper cutoff frequency. We learned that if we want to design something that has a high cutoff frequency, sometimes we have to change the op amp, going from a 741, which is slow op amp, limited op amp, to a 411, which is a faster, more expensive op amp. Sometimes we have limitations, and I've mentioned this again. Sometimes we want a large bandwidth, but at the same time, we want a high gain as well. Okay, but these two contradict each other. If you have a single stage op amp, increasing the resistance in the feedback would definitely increase your gain, but at the same time, because the F2 is equal to GBW or gain bandwidth product over A noise, increasing that A noise or the overall gain would definitely reduce your unity or upper cutoff frequency. So again, if in this system I increase R2 or the feedback resistor, I would increase AV. If R2 increases, then AV increases. But when AV and assume that this is a non-inverting amplifier, and when AV or A noise increases, F2 decreases. So increasing the gain reduces or decreases the frequency response, and reducing the gain or R2 increases the frequency response or F2. So there's a trade-off. But what if we need a system which is high gain and also has a wide frequency response? So we want to maximize F2 and we want to maximize the gain. How can we do that? Obviously, we can change the op amp, but that has a limitation. We don't have an op amp that would have like an infinite gain bandwidth product. They are limited to around like 20 megahertz, something like that, for normal commercial use. So one way is to change this, but this gain bandwidth has a limitation. Another way that we can address this is by simply having a multi-stage op amp amplifier, and we solved it for this one. So when we solved this, we realized that for a multi-stage, each stage has its own upper cutoff frequency. One was 135 kilohertz, one was 330 kilohertz, another one was 250 kilohertz. Okay. And the limit, the upper limit of the system would be equal to the upper cutoff frequency of the one with the lowest cutoff frequency, which is 125 kilohertz. You may ask, so what is the benefit of using multi-stage? What is the benefit of it? What do you think is the benefit? We already calculated the gain for each stage. Gain for the first stage was 8, second stage was -2, and the third stage was 4. But what is the overall gain? What is the total gain of the system? What is the total gain of this op amp? Yes. So as you remember from, I think it was the second week, when you have multi-stage op amps, the total gain, I'm going to mention, A total would be the product of each stage's gain. So we will multiply the gain of each stage. So in this particular example, the gain of the first stage is 8, second stage is -2, third stage is 4. So what is the total gain gonna be? Negative 64. So we can see that the frequency response is the same as the first stage, but we have a significantly larger gain and the output voltage.
Then it works out good with the frequency too.
So the frequency, no, it doesn't work. The frequency, you always pick the one with the lowest frequency. But what happens if all the frequencies are equal? Then we have another problem, and I will tell you how we can find the upper cutoff frequency. So to solve the problem, we can have a multi-stage op-amp. Having a multi-stage op-amp would multiply the gain, and then we won't have this limitation on the gain, as I mentioned, the limitation on the overall gain. Here, we can have, technically, when you add those gains, we can have the same frequency response of one of them, but you're going to have a much larger gain. So now it's going to look like this, and I'm going to draw it with this bluish color. Now the frequency would be like this. The gain is significantly higher, but the frequency is still around the frequency of one of those stages. So this is one difference. You multiply them, you multiply the gains, you have the cascading effect on that, but the frequency response remains the one at upper frequency. Something else is happening here, and it's a drop after that. So here we have a drop of 2 dB. If we have 2 stages, we would have a drop of 4 dB. For example, 3 stages would give us, I'm sorry. 1 stage is a drop of 3 dB, 2 stages a drop of 6 dB, and 3 stages is a drop of 9 dB. I confused with the 2 dB drop and the amplitude. So the slope that this drops for a single stage first order is 3 dB per decade. If we have 2, it's going to be 6 dB, and if we have 3, it's going to be 9 dB. So you can see a steeper decline, a higher slope when you add to the number of stages, or when you cascade them. So as mentioned, the total overall gain is going to be negative 64, which is much higher than any single stage. But the break frequency is going to be 125, which is the cutoff frequency of the stage with the lowest cutoff frequency.
Doesn't never have lower break frequency as well thing.
Yes, so that's a very good question. This one, because we don't have any coupling capacitor, the lower cutoff frequency would be 0. So the frequency response starts from 0 hertz, because we don't have any coupling capacitor. But if we add a coupling capacitor in each stage, like example, imagine we have one here, another one here, and another one here. And we calculate the cutoff frequency. This one is a complete different equation for lower cutoff frequency. You have to measure the RC tau. And imagine that we have already calculated the cutoff frequencies, the lower cutoff frequencies. This one has a 4 hertz, this one has a 10 hertz, and this one is a 50 hertz. Which one is the cutoff frequency of the system? 10, 4. So the graph would look like this. Let me draw a. So now we have 3 different op amps. One op amp is between 4 and how much was it? Let's say 125 kilohertz and 4 hertz. The other op amp is between 10 and 250. And the third one is between 50 and 333. So for the upper cutoff frequency, we will pick one with the highest. And for the upper cutoff, so lower cutoff frequency, we will pick the one that has the highest upper cutoff frequency, and for the upper cutoff frequency, we will pick one with the lowest upper cutoff frequency. So now our frequency response would be between 50 hertz and 120 kilohertz. Because if I have a frequency in this point, this would act like a filter and filter it out, okay? So we have the common region. The common region would be our frequency response. And we want, like I would say 90% of the time, you won't have something like this. You usually have one coupling capacitor, and that's at the beginning of the first stage. And that determines our lower cutoff frequency, if we have any. If not, most of the time we don't care about, unless we have a 60 hertz, like a humming noise that we have from the outlets, we don't want to even put a lower limitations on the op amp. Yes.
So this capacitive coupling makes our frequency range smaller.
Yes, always. If you add a capacitor, you always limit your frequency response. And there are some limitations and also big benefits to this. Let me give you an example. So one example, yes, please ask your continue question so I can. Yes.
Like a radio, if an antenna picks up all frequencies, you want to filter it out.
Yes.
To just get one little section, one small range of frequency, you can use that.
Yes, perfect. That's a great example. And that is actually called what we call a notch filter or a bandpass filter. So one good example, as you mentioned, and I'm going to give you a couple of examples. This is also in signal systems and communication systems. When you have, like, for example, an FM radio, any type of, microwave frequencies, radio frequencies, and so on. And imagine you have an FM radio, and this FM radio, you have different stations. One is in 10 megahertz. Another one is in 4 megahertz, 14 megahertz, for example. Another one is in 200 megahertz and so on, okay? If we do not have a filter and we have an op amp that covers a wide range of frequencies, what is going to happen is you're gonna pick all these signals at the same time. And it's going to overlap, and in your speaker, you're going to hear 4 or 5 stations at the same time, which is, you can't get the information that the data that you need. It's going to create data distortion and actually destroy your data. So what is actually happening is, you're correct. We are using a op amp with a limited frequency response, which looks like this, or a transistor or whatever. And this has a frequency response between, let's say, 2 megahertz and 2.4 megahertz. And this is exactly what happens. But this is not a fixed filter. We call this a bandpass filter. This is a variable filter. We can move it left to right. Imagine you have a knob, and that is actually a resistor potentiometer. Changing the potentiometer changes the impedance and changes the frequency. And imagine that you can actually move this to the left and right. When we want to pick up frequency, for example, 10 megahertz, we will first put our filter here. We will pick this and eliminate everything else. Then we will move our filter, for example, to the 3rd station. So the knob, when you're moving that knob, you're moving a resistor, you're changing a potentiometer, for example, or a variable capacitor. And by that, you're changing the upper and the lower cutoff frequency, you're shifting your filter. And this is called a bandpass filter. If we have something that, another scenario is that, imagine you want to pick this and this station, but this in the middle is noise. Then we can use something which is called a notch filter or a band stop filter, which is going to stop a certain band and pass other frequencies. One example that I've worked with a lot is with EKG, what we call it EKG or ECG, electrocardiogram devices. Electrocardiogram uses an op amp to amplify the voltage between 2 leads. Those 2 leads are usually connected on your arms, Same thing when you have your Apple Watch, when you put your finger on the volume knob of an Apple Watch, and measures your heart rate. EKG or electrocardiogram measures the electric signals which are coming from your heart. And it could detect if someone is having a heart attack or arrhythmia. It's a very, very useful, important tool. It's been out there for almost 100 years. So the way that electrocardiogram works is that our heartbeat is about 1 beat per second, or we can say 60 beats per minute, something like that. So the frequency is around, I can say 1 hertz. Yes. But the thing is, a lot of equipment that we have around here, like these transformers, these electric devices, they create a same frequency, around 2-3 hertz. As long as your heart rate is around 1 hertz, normal heart rate, it doesn't have a problem on capturing the data and getting the signal. But when someone is running, for example, the heart rate elevates, goes up to like 140, 150, sometimes close to 180. And that is the frequency which is closer to these power lines and so on. And those frequencies, which comes from different inputs, your watch itself, the EKG device, acts like a big antenna. And if you have an outlet around you, that outlet is actually going to act like a transmitter, and your EKG device acts like a receiver. It's like a big antenna, and that's another antenna. And all around you have this magnetic field. Inside these walls, you have wires above you. All these are creating noise. And if that noise interferes with the signal, then you're going to have the data is going to be distorted. If a doctor is looking at it, they may think you have someone has arrhythmia or having heart problem. So it's very important to have a very, very clean, especially in biomedical and medical applications. So what we do is we use this notch filter. And the good thing about these outlet frequencies, like the 60 hertz, is that they are fixed frequencies. So we would add a notch filter to these type of circuits to filter out certain frequencies, like 60 hertz or something like that. But if you have a variable frequency, that's going to be a adaptive, with what we call adaptive filters. It's going to be very expensive, much more complicated. But this is an example of a notch filter. Bandpass filter example is going to be radios that you have, radio receivers. Notch filter is the opposite. We're going to spend 1.5 to 2 weeks. One chapter of this class is just dedicated to active filters, active low pass filters, bandpass filters, high pass filters, notch filters, and so on. But this is just because you brought out the question. I wanted to just give you a picture, but that is exactly accurate that, yes, this is used as a filter type of filter for different type of receivers. But we're going to get in depth again towards the end of the semester. We have one chapter, chapter 9, that is dedicated to this. So let's go back. So we have a system, has some limitations. We want to increase its gain. To increase its gain, we will build a multi-stage op-amp. But the multi-stage op-amp, the upper cutoff frequency is going to be equal to the lowest upper cutoff frequency of each stage. And the overall gain is going to be the multiplication of all the gains. When we add 2 or 3, then the loss would increase. It goes from 3 dB to 6 dB, 9 dB, and so on. But what if we have 3 stages and all 3 stages have the exact same op-amp, which would result in the same gain bandwidth product and the exact same gain? So you imagine we have 3 identical stages. Let's go back to this example. So imagine we have 3 stages of op-amps connected to each other in cascaded, and the A noise for the first one is 5, for the second one is 5, and the third one is 5. So A noise for all of them is 5, and the gain for all of them is also 5, for example. All of them non-inverting op-amps, exactly the same all three using LM741s. And the cutoff frequency for all of them is, let's say it's 250 kilohertz. 250 kilohertz and 250 kilohertz. So something interesting happens here. Here, the overall gain again is the total gain is the multiplication of each gain. So 5 times 5 times 5, it's going to be 125. But the cutoff frequency is no longer 250 kilohertz. So we can't pick, all of them are the same, but we can't pick one of them as the upper cutoff frequency. In this case, the upper cutoff frequency is determined by this equation. And for this equation, let me go, I think I'm going to show you this, the final equation that we have. So for this system, the upper cutoff frequency of the system itself is going to be equal to F2, which is upper cutoff frequency of one of the system here for that example was 250 kilohertz. Square root of 2 in the power of 1 over n, and n is the number of stages. So in that particular example, n was 3. So instead of just picking one of those upper cutoff frequencies, we must use this equation for the upper cutoff frequency of the whole system. And for the system, the upper cutoff frequency for the system is going to be the upper cutoff frequency of one of the stages times square root of 2 in the power of 1 over n minus 1. So I'm just going to go back again. This is the proof for that. Again, if we make a few assumptions about the exact shape of the roll-off curve, we can reduce this to a simple equation. The response for a large network may be determined to be AB is equal to 1 over square root of 1 plus F2 over F2C, which is the systems. Where F is the frequency of interest and FC is the critical frequency. It is more convenient to write this equation in terms of normalized frequency of interest. Instead of being expressed in hertz, the frequency of interest is represented as a factor relative to FC. If we call this normalized frequency Kn, we may rewrite the amplitude response equation. And when we solve that, 1 over AB is going to be square root of 1 over Kn in the power of 2. And when we solve it for Kn, it's going to be equal to square root of 1 over A squared minus 1, and An would be 0.7 of that for a single stage. For multi-stage, it's going to be AB, it's going to be 0.707 or 3 dB of in the power of 1 over n. Because as I mentioned, the 3 dB drop is equal to 0.707 or square root of 2 over 2. So negative 3 dB. It's actually the drop that you have in the amplitude. So if this is the maximum, you're going to have 3 dB drop. This is going to be the 3 dB drop in the system. Okay. Now, a practice problem. Imagine we have a 3-stage amplifier. They use identical non-inverting amplifiers. The gain is of each stage is 10. If the op amp uses have a unity of 4 megahertz, what is the system gain and the upper cutoff frequency, break frequency? So because it's a non-inverting amplifier, the upper cutoff frequency would be F unity over A noise, which is 4 megahertz over 10, which gives us 400 kilohertz. And now the cutoff frequency of the system will be 400 kilohertz times square root of 2 power 1/3, because we had 3 stages. 3 op amp. And finally, F2 of the system would be 203.9 kilohertz. Let's solve now a few practice problems. Imagine we have a multi-stage op amp. This is positive, negative. Oh, let's make this negative and that positive. Easier that way. Negative, positive. Positive is connected to the ground. So all of them are identical. All op amps are a UA741. This is 25. This is 150. I forgot one part. Just give me a second to fix it. This is 12, this is 2. This is 24, this is 4. We want to find the total gain, and we want to find the F2 of the system. And if Vin is 2 millivolts, what is V out? So A, the F2 of the system, and also V out. Did you all solve it? You need more time?
The formula for finding F2 in the left case.
What's the? What's the hertz in the first one?
Gain bandwidth product over A noise. Did you solve it? What is F unity?
System.
Mm-hmm. Mm-hmm. I think I haven't. So let's find A noise for the first one. What is the A noise for this first step? It's gonna be 150 over 25 plus 1. Am I correct? So it's gonna be 7. What about the second one? It's gonna be again 7. And what about the third one? 24 over 4 plus 1. Again, it's gonna be 7. Since all of them are in the LM741, they share the same gain bandwidth product. And for LM741, as mentioned, it's 1 megahertz. You need to memorize this. This is very important. So F2 for each of them is going to be 1 megahertz over 7, which gives us what?
40.
Yes, 143 point something.
It's 142, 142.
Yeah. So let's round it up to 143 kilohertz. Yes. What is the gain of each stage? Yes, the first one is negative R2 over R1, which is -6. Second one is also -6. And the third one is also -6. So the total gain would be equal to -6 times -6 times -6. So 36 times 6 is going to be, yes, -260. So this is overall gain. What is the output voltage? It's going to be the input voltage times the gain, which is -216. So it's going to be 2 times 216, going to be 532, -532 millivolts, or in other words, 0.532 volts, which is an acceptable range. Anything above 14, 15 is gonna. What about the F2 of the system? It's going to be equal to, using the equation, it's going to be equal to F2 of each stage, square root of 2 over 1 of, in the power of 1 over n minus 1. F2 is 143 kilohertz times square root of 2 in the power of 1, and we have 3 stages minus 1. So what would this be equal to? What do you have? 73?
I didn't, when I did my F2 of the system, I didn't round my 143 kilohertz, I did 142, 857.
What is your answer?
72.
72 point? And yours is? There shouldn't be that big of a difference. Yeah, the difference for rounding up, it's not showing. So let's imagine that we rounded up to 143. It was 172, yes? Okay. Yeah, can you double check this as well? Please double check the math. Okay, thank you so much. Okay, that's it for today. I'll see you on Tuesday, and as I mentioned, Tuesday we're gonna have the lab. Yes,
So do you ever find your A noise total, or is it always?
that's,
a piece?
no, we don't need the A noise total at all. We only need the total gain of the system. Yeah, that's a good question. Okay, thank you so much. Have a great weekend.
Oh, then our test, that's about Tuesday?
Tuesday, you're gonna have a, for you, for the in-class, you're gonna have the lab. Thursday, you're gonna have a review session, and the next Tuesday after that is gonna be